Okay, so two sides of a triangle have lengths 12 meters and 15 meters. The angle between them is increasing at a rate. So increasing at a rate of 2 degrees per minute. In this case, they're given to us in degrees. How fast is the length of the third side increasing when the angle between the sides of fixed length is 60 degrees? Okay, so we're supposed to use law of cosines, which is a nice little formula they're giving us. I guess we have one side that's 12 meters and another side that's 15 meters. Those are fixed, they say, so they're not going to be changing. The angle between them, that's the angle between them, is increasing at a rate of 2 degrees per minute. So I guess d theta dt is given to us. The rate is given to us as 2 degrees per minute. I guess the sides are opening up and the angle is increasing. How fast is the length of the third side? So this is the third side. And if the angle is increasing, so it's becoming wider and wider, that means the side across from it is also changing. And so let's call that, I guess, what do you want to call it? Call it A based on the law of cosines that the hint gives us. So we'll call that A. And how fast is that third side changing? That means I'm looking for dA dt. What's the rate of change of that side as the angle is opening up between them? When the length, besides, when, what are we? Oh, hang on. When the angle between them is 60 degrees. There you go. When theta is 60 degrees. And remember, degrees, probably we're going to use them in unitless measures. Pi over 3 is 60 degrees. All right, so law of cosines, basically what they're giving us here relates the sides. I'll call that, I guess they're calling it alpha. I'm going to call it theta. It's okay. This is B, this is C. So it's always the side across that angle is equal to the sum of the other two sides minus double the product of the sides and cosine of that angle between them. So they called it alpha, I'm calling it theta. So in our case, since we know the fixed sides, we can plug those in. And we know the A is changing, I'll leave it as is. So I'll say 12 squared for maybe B is this one, C is this one, plus 15 squared. Again, I can plug them in right in the first step because they're not changing, they're fixed. Minus 2, B is 12, C is 15, cosine of theta. So leaving theta and A changing because those are the two items in the problem that change over time. Simplify those, we get that equation. So square everything, add them. Now we're ready to d dt both sides, differentiate with respect to time. So we'll have 2a dA dt because a is changing with respect to time. This guy goes to 0, it's just a constant. Then we have negative 360 times this guy goes to negative sine theta. And remember, theta changes over time, so pop out chain rule d theta dt. Which means I have 2a dt and then a positive 360 sine theta d theta. We can divide everybody by 2, I guess. And we end up with a dA dt equals 180 sine theta d theta dt. Now I'm ready to plug in the knowns. We know the angle is pi over 3. We also know d theta dt is 2 degrees per minute. Let's go change that to radians per minute because everything we punch in here has got to be sort of unitless because ultimately I'm looking for dA dt, right? Yeah, so I'm looking for dA dt and I want to deal with it, I guess, with meters per second because this was in meters. So let 2 degrees is going to be, if I put it in radius, pi radians is equivalent to 180 degrees. So these guys are going to go away and I'm going to have pi over 90 radians for my d theta dt. So now that's just a real number. So I'll plug in this guy as pi over 90. And we know the angle is pi over 3, so we could do that also. Sine of pi over 3. We'll punch that in. dA dt is the guy we're looking for. A we don't know, but we can get it. We can get A, that long side, because we know at that moment the angle between them is pi over 3. So let's go on the side here. I have the 12, the 15. This is fixed at that moment as 60 degrees or pi over 3. This is the guy we don't know. So we can apply law of cosines to get A. Remember, A squared is 15 squared plus 12 squared minus double their product times cosine of that angle, which is pi over 3. Once we punch that in, remember to have your calculator in radians when you're putting in pi over 3. If it's in degrees, then you can put the 60 degrees. So A must be square root of 189. So here we have square root of 189, which means dA or dA dt is going to be 180 over square root of 189 times sine of pi over 3. Again, your calculator in radians times pi over 90. So once we punch all of that in, we're going to get dA over dt approximately 0.40 meters per minute. So that side across that angle is changing at a rate of about 0.4 meters per minute at the instant when the angle between them is pi over 3 or 60 degrees.